So my name is Molly Anderson. I work as a life support analyst, doing simulation, trade studies, and conceptual design at Johnson Space Center. Bob has given you sort of an overview of environmental control and life support systems, and this afternoon you're going to get more details about each of those systems. So what I'm going to walk through is sort of the process to use when designing the system, because I don't want to give you an answer about what a mission to Mars should look like, because I think the whole point of these activities is to come up with something new and break out of our assumptions about what we think it might be. But at the same time, you're probably going to have to go through a similar thought process. So I'm going to walk you through the major questions you have to address when you decide what a life support system for Mars is going to have to be. I'm going to talk a little bit about how we make decisions, which I think we'll get into some of that. I'll start to touch on that sort of value analysis, and if people want to talk about that more, we can go into it. And then I'm going to briefly talk about architectures we already have. And then I have some references in the back for people who are starting to ask quantitative questions and things like that that may help. Okay, so you're defining a life support system or designing one. You're not, well, I suppose you are. You might be doing it in a vacuum, but we're all subject to the constraints of the mission, the goals we want to achieve, and things like that. So the first step of the analysis is going to be define the mission and the vehicles, and sometimes this is harder than you might think, and there can be pretty significant variation. You can identify fairly easily the functions that have to be performed for the crew member. You know, Bob kind of started with those air, water, waste sort of things, and of course you can just break them down into many sub-functions. And then you have to decide how you're going to perform those functions. How are you going to get the resources that you need to give the crew their best chance of survival? And then finally, since the word ultra reliable has shown up in these topics, how are you going to make sure, like Bob said with the ISS, that you have a robust system? What is your response to a failure or a contingency? And that also depends on the mission. So I'll talk about that a little bit. So mission and vehicle definition. The first question is always, what is the timeline for me? For a Mars mission, obviously we're looking at a pretty long timeline, but probably not as long as space station. A spacesuit even counts as a life support system. You know, we have that lovely picture. Everything to keep that person alive is contained there. So really a spacesuit counts as a vehicle in a lot of ways. But there you have that ultra short duration. You know, and then we have intermediate durations. So hours, days, weeks, years, generations, those are all really significant differences in the class of life support system that you're going to select. Next, you need to start thinking about the characteristics of the vehicle. We're focusing on the life support system here, so we assume that someone else is sorting out structures and propulsion and things like that. Propulsion can determine both what other resources are there and the timeline, but also we start to talk about systems now where a transit habitat to Mars may be pre-deployed with a slow propulsion system, and then use chemical propulsion to do some things fast and then go back to slow propulsion. We need to think about the gravity or microgravity environment. Not all of our spacecraft have to be microgravity. Some things have to be both. Like Bob said, they went to a lot of trouble to balance out the space station hardware when they were trying to test it on the Earth to not get pressure heads. So if you have a system that has to work both places, you have some pretty significantly different dynamics. We had some questions earlier I heard about like biological systems. There are a lot of municipal water treatment systems that use aerobic microbes, but it's a whole lot easier to generate a healthy aerobic system when you can bubble oxygen or air through and trust that it's going to come out the top and the wastes are going to come out the bottom. And that's nowhere near as easy in space as it is on the ground. And then finally, when we're rarely talking about a single life support system. When we're talking about a Mars mission, there are probably a lot of pieces. So all of these sort of pictures could be assembled together for a Mars mission. The Orion crew capsule has the heat shields for re-entry and is man-rated for, or would be man-rated for, launch from the Earth with the crew. So you're going to have to use that to get to and from the Earth, to low Earth orbit. You're probably going to need both microgravity and gravity-compatible life support systems, whether that's the same or whether that's sort of an in-space piece and a surface piece. That depends on your mission. You're going to need a lander and an ascent stage of some sort to get to and from the surface of the planet. And then you're going to want to do something when you get there, whether that's with rovers or with spacesuits. If you've gone to all the trouble of sending people, you want them to be able to explore and to do the science and all that sort of stuff. So each of these pieces has a life support system, and they all are interconnected. So you have to think about all of them at the same time to some extent when working on your design. Just review a little bit. Bob already introduced some of these. So the life support people, I always say, are kind of lucky, because when we look at all these different missions, our requirements stay a lot the same. It's basically, don't kill the crew members. And the things that a human being needs to survive stay pretty consistent. We need pressure. Hopefully some of that pressure is oxygen. We need to remove the contaminants that are generated. We need clean water for a number of different purposes. We need food, though we don't usually consider that part of the life support system exactly. It comes into play in a lot of our decisions. And we need to deal with our wastes. Bob had the picture of the ins and outs. Anything that comes out of the human body in a closed environment has got to be dealt with in some way. Whether that's urine and feces, or microbes in your sneezes, or skin cells sloughing off, or gases from your skin or your digestive system, anything. All of that has to be removed. And then, even though the environment is the same, the functions that the vehicle has to provide in order to maintain that environment vary depending on, like I said, duration and degree of independence, right? So my comparison example is sort of going on a hike versus going on a camping trip versus a major expedition versus really colonizing a new place. And you can go through these thought processes yourselves. How long, what do you have to bring on each of these, and how long can you go without, we assume air in reasonable temperatures for most of these, but there are mountain expeditions, I guess, even you could include in there where the oxygen is not necessarily guaranteed. But so you can walk students through, or just as a thought experiment yourself, think about how long you can last without each of these things, and what kind of classes of missions would have each of them. And then when we've looked at previous exploration of our Earth, what is the risk that is acceptable? What is the importance of survival versus the importance of achieving exploration goals? I'm going to assume that survival ranks pretty high, but that hasn't always been true in the history of human exploration. And if you've expended so much effort to get there, how much can you sacrifice in terms of your exploration capabilities in order to ensure survival? You know, are they of equal value, or is one more important or less important than the other? And so that gets into reliability. You know, when you think about reliability, how much of it has to be robust? Is it just the survival, or making all of your goals? Other life support system functions. So besides the crew, the life support interfaces with a lot of other vehicles. We end up providing water to thermal systems around the vehicle, to thermal systems in the EVA suit. We provide oxygen other places. We provide medical resources, things like that. And we may get wastes back from these systems that are different from our nominal crew member wastes. We've been talking about closure too. If you have a lot of exploration and EVA activities, those vehicles are usually optimized to be lightweight, right? And they don't want to bother expending the resources in mass and power in order to recycle wastes there. They may not want to bring it back. They may not be capable of bringing it back. So you can't close a system and recycle your wastes if you didn't get the wastes back in the first place. And depending on the type of the mission, that can be a pretty big deficit in your mass balance. So once you've gone through the functions for keeping the crew member alive, you have to start allocating them out, but you won't really be able to determine your full list of functions until you've done the trades on where you're going to get those things. Your logistics can come from Earth, either the stored consumables, oxygen, water. They can be regenerated from your wastes, or they might be provided locally. None of these should be assumed to be easy, right? It seems like logistics from Earth is a highly reliable solution, but you still have to maintain the quality of those resources, and you know, storing water without it going bad, storing oxygen without it leaking away, is not necessarily a guaranteed success. We'll talk probably more about recycling and regeneration later this afternoon, but also you can think about the in situ resource utilization as an option. You know, we have ice caps we talk about. We have resources on Mars that could be converted into oxygen potentially. So those could be in the trade space, but they all have their own risks. And people have been asking, you know, I heard, how does the exercise increase the metabolic rate, and things like that. I've got a link at the end to this Human Integration Design Handbook, which is a publicly released NASA book, which goes into probably more detail than you wanted to know on the functions that the life support systems are required to provide, as well as some habitability stuff and things like that. But it has a lot of those quantitative lists of consumables you have to provide, the range of conditions that you have to maintain for carbon dioxide or oxygen, for off-nominal and nominal situations, and things like that. So hopefully that'll help people out.
Hey, Molly. The
Yes.
other thing I want you, this is Charlie Camarda. The other thing I'd like you to think about is any time you have some simple modeling tools that we could post, that we could take advantage of, that students and teachers could use to do some experimentation in the design and trade space that we could possibly link to and things like that.
Okay. We can have that conversation offline. We have some tools we've worked with other university levels before. Simple is the dangerous word.
Right. I understand.
But yeah, we can certainly talk about that. Resources. So in order to provide those functions, you're going to need to tally up the quantities of resources you need. When you make these decisions, you know, if it's mass-based or cost-based or whatever, you start getting really picky about quantities. And small changes in the quantity of water, for example, can make a difference. Air is fairly easy. It's usually metabolic based, but if you're going to be doing UVAs or things like that, those are going to increase. Water. We use water for a lot of different purposes on Earth. Obviously, the crew is going to need to drink water. That one's pretty easy. Then we start getting into what else do we use water for? Hygiene. If you look at the Human Integration Design Handbook, it's kind of oriented towards sort of crew exploration, vehicle activities, and things like that. So the amount of hygiene that the crew members get on space station and that they'll get in the CEV is pretty low. Right now it's 400 milliliters of water a day for all of your hygiene purposes. There are no showers on the space station. But if you're going to be doing a Mars mission and you're going to be dealing with dust and you're going to be dealing with EVA suits in a gravity environment, you may need to think about more serious hygiene. Also, if you're in a gravity field, it may be a lot easier to trust that when you pour water on the top of your head, it will indeed run down to the drain. So a more thorough hygiene system may be feasible. But those are decisions that you have to make about the vehicle and make about the mission before you can fully design your life support system. We also talk about laundry. Clothing is a resource that can be recycled. We don't do it much other than, I think there's one picture floating around the internet of Bauer Sox with his shorts in a Ziploc bag full of water trying to wash his favorite athletic shorts, but officially there is no laundry on the space station. But with these Mars trajectories, unless you're opening up to a change in propulsion, are going to be pretty long, and starting to recycle clothing and habitation supplies, with laundry and things like that, could get you a lot of value back. Food. Obviously, everyone is going to need food. We right now supply a mix of dehydrated and stabilized natural form foods. The food system that you choose can have a big impact on your life support system. If you are growing food, which I guess Ray may address a little bit tomorrow, you have a whole other life support system for your crops that you have to deal with. If you are trying to minimize mass by sending highly dehydrated food, now you've gone back and increased the water required for that purpose. Food can change, food quality or the mix of carbohydrates and fats and proteins can change the wastes that come out of the human body and the loads that each piece of your life support system is going to have to deal with. Habitation. I heard and saw Larry in the room. Having a habitable environment isn't exactly something that you can load in a crate on a ship, but the way that you operate your system will impact it. We think of free volume as a resource, and you need to deal with your wastes to both keep that volume free and keep that volume at a quality that is usable. We had some semi-serious and semi-joking moments in a meeting yesterday talking about, would you put your microwave in your bathroom? And in a lot of spacecraft, you don't really have an option. Everybody is trapped in a space about the side of the bathroom, and that's where everything is happening. And for the long term, most people are not going to find that acceptable, and they're going to find it hard to do their job successfully. What kind of impact does that have? Okay, so in this process, if you've added up all of the resources you need, you have to think about how you can get them. Even on a Mars mission, there's a lot of stuff that's going to be sent from Earth. The first question is there any way to get this resource besides sending it from Earth? Nitrogen is a classic example of something that's really the only option we consider. The human body doesn't really generate waste nitrogen that we can recycle. We lose nitrogen pretty much from leakage, overboard venting, things like that. And so there isn't really a waste you can get it from. And when we're looking at Mars, I've never heard much about any ISRU processes that are going to generate nitrogen. And certainly when you're in space during the transit part, it's not like there's any that you can harvest. And then you can start looking at the things that could be recycled. Water, oxygen, food. And now is where you enter the trade space. Is it more cost efficient to recycle it, to generate it from the local resources, or to send it? And cost is in quotes because you have to decide what's of value to you. Like the dollars usually fall away. We're usually talking about mass. You may be talking about reliability. You may be talking about volume. You may be talking about power consumed. All of those things need to be considered. Recycling. When we start to think about how we can produce a resource, there are a lot of different sources of waste which may or may not all be equally valuable. Condensate water is essentially already distilled because it's been taken from humidity and condensed back out. So that's a very clean water source. So like Bob said, the Russians use that to power their oxygen generator because it's a relatively easy resource to recycle. When we get all the way down the chain to feces, there is water in your feces, but that is a pretty complicated process to extract. Beyond the contamination and the psychological yuck factor, we're dealing with at least 3 different phases there. Solids, liquids, and gases. Managing that separation of microgravity is very complicated. Oxygen. Bob talked a little bit, he talked about the oxygen generator, and we've talked a little bit about the different options available for CO2 reduction. The Sabatier reactor that gets partial closure, Bosch reactors. There's concepts for electrolysis of carbon dioxide directly, which is useful potentially both for recycling and for in situ from Mars. But most likely after you go through this analysis, you're going to start to consider hybrids, where you have some shipped from the Earth, some provided, or potentially you ship a resource from the Earth that enables you to recycle something else. We've looked at systems or potential for, say, using the Sabatier reactor, which vents methane and loses some hydrogen overboard, and shipping hydrogen from Earth. The cost of cracking the methane back into hydrogen right now is relatively high, though definitely people are working on that. And so there may be a decision you have to make where you bring part of your recycling resources with you in order to make the process go to completion. Bob has talked about the consumables in the space station system, like the multi-filtration beds. Lyo canisters are an example where they get consumed. But besides just hardware, there are also chemicals you have to introduce, fluids, things like that, that you have to bring with you in order to make your recycling work.
Hey, Molly, I don't know if you're familiar with the NIAC study that was looking at a different makeup gas. They were looking at using argon if you were going to Mars as opposed to nitrogen. I don't know if you know of it or if you can comment on it or...
Absolutely. Bob talked a little bit about the atmospheres that the different vehicles have used, the nitrogen, oxygen. The human body definitely needs oxygen. I think we have some evidence that that some nitrogen is good for the body. It doesn't really get consumed. It just kind of hangs around. But nitrogen doesn't have to be the only diluent gas. We've moved away from pure oxygen systems because of the fire and flammability risk. It's just too extreme. And if you're going to especially for a long mission where you need more habitation accommodations, you're going to have a hard time finding non-flammable options for all of them. So we have looked at argon is certainly something that could be considered. It is, another gas that is not going to interact much with the human body, but would keep your flammability risk down. Another model is saturation divers. Saturation divers, when they're underwater, is sort of the inverse of our reduced pressure systems. They're at very high total pressures, but they need to keep the oxygen a very small percentage of that total pressure. Your body's equilibrium is driven by the partial pressure of oxygen and carbon dioxide around you, and that's what drives transfer back and forth across membranes and things like that. So if you keep those partial pressures constant and change the amount of nitrogen, you can end up with a pretty significantly different percentage carbon dioxide or oxygen. So saturation divers use helium a lot of the time. The helium, it's a small molecule. I think it's easier for it to come out of your blood, so you don't get the same decompression sickness risk. So yeah, there are definitely other options in dealing with gases. At NASA recently, we have not had a lot of luck because of the lack of medical research with those diluents. And like Bob said, in the face of radiation, for example, things that we got away with for short missions, now they're like, oh, you need to maybe back off on CO2 or back off on something and keep the crew very safe, because there are some risks that we just can't do anything about, so we might as well control the ones we can. And so they haven't been super friendly to going to those other diluents because they just don't have the body of research to know what it's going to do to the crew member and what the side effects when mixed with microgravity or radiation exposure are.
Great. Thank you, Molly.
Okay. And then when thinking about providing resources, closure versus recovery. This is sometimes a soapbox of mine. When you talk about a closed life support system, you have to be very clear about the difference between closure and recovery. To me, closure is a question of how much of the resources that you've just inventoried are going to come from a recycled waste. Okay? Recovery is a question of how much of the waste is converted to useful product. You do not necessarily need to have a 100% recovery system in order to have a 100% closure system. It seems a little bit confusing at times, but usually it's because there are things not officially defined as part of the life support system that are sneaking resources in, usually as the form of wastes. So we talked about food, right? Even dehydrated food has some water in it. And the human body will convert your carbohydrates and your fats and your proteins into carbon dioxide and water. So you end up with more water leaving the human body than you put in. And you definitely end up with more wastewater leaving the human body than you provided as potable water, out of your potable water dispenser from your tank. Another example here, I have wet supplies. We talked about these small quantities of hygiene water, and the crew gets through that by having a lot of wet wipes. There are a lot of Huggies wipes sent up with the potty. There are a lot of alcohol wipes, there's not alcohol wipes, but there are a lot of antimicrobial wipes used to clean surfaces, and all of those things are wet. And so each of them is a tiny little secret tank of water. If you leave that in the environment, it's going to evaporate out, and you can condense that water back. So you may get more available as waste than you need to provide as clean product. So don't assume that you have to recover everything in order to get closure. But then we have the costs on the other side. Most of our EVA technology to, well, I mean, I think it's fair to say all of our EVA technology to date has used phase change of water as the primary cooling method. The Apollo suits and the Space Shuttle era EMU suits used a sublimator. They actually had a little bit of recycling going on inside there because they could take condensate from the crew and put it into the sublimator to evaporate. Now we're looking at a membrane evaporator. But the amount of energy that you can reject through phase change water is just tremendous for the amount of mass that it costs to do it. So when you're trying to be lightweight and travel, it just totally wins. But that's water now that you're taking out of the life support system that you don't get a waste back that you can recycle. So that can happen directly in the suits. It can happen with another vehicle, like providing that same thing for a rover or something. It can happen in your vehicle. When we've looked at analysis of the Orion vehicle circling the moon, when you're on the hot side of the moon, you can't. Your environment is so extreme that you can't use a radiator successfully to reject all of the heat from the vehicle. You know, if the outside environment is hotter than you want to be, you need to turn off your heat transfer. No amount of larger radiator is going to fix it. So they need to use water evaporation during those hot phases. Mars, conveniently, is somewhat more moderated than the moon. The hots aren't as hot and the colds aren't as cold. So you may not have that issue, but you may look into it for contingencies and things like that. Any questions on that? No? Okay. I saw Charlie push a button, but not ask something.
You're watching me. You can see me. We just can't see you, Molly. I just wanted to comment that was an outstanding comment you made at the end there, because I happen to be an old heat pipe person, and obviously I understand the benefits of phase change, and that was a great example of a multifunctional use of the water to actually be a very efficient mechanism for transferring heat, and thanks for bringing that up.
Yeah, no problem. Okay, so the next question you have to ask yourself, so you've decided what your functions are, you've decided how you're going to provide them, and the next question is, what are you going to do when they fail? And I know you're tasked with a reliable system here, but you had better assume everything can fail. Some of those things can be repaired. You need to think about, how are you going to design your reliability? Are you going to make sure that every component is as reliable as possible and say that if it fails, we accept that? At some point, you may have to accept loss of life. Not that these things are going to happen, but if enough meteors or micrometeors strike the vehicle, there's a point at which you can't do anything about it. So you have to accept that, and then you have to figure out where to draw the line. But most likely, you will have backups for a lot of functions. And so you can institute your reliability, or you can make your reliability happen at the system level or at the functional level, as opposed to assuming that you can somehow engineer a magic component that never fails. So let's think about a system. You have to consider, how is your system going to fail? I have gracefully versus catastrophically. When our air conditioner starts failing in the house and the compressor starts to go, a lot of people start to notice, it's just not cooling the way that it used to. And so you have a period where it's not working as well, and you can respond to it, and you can figure out what component is going wrong. And then we have the day where the fan just shuts off completely and there is no compression. So you think about, how are you going to detect what's going wrong in time to intervene? this starts to get in really to your technology choices. And then you can look at, if you have a failure, how long until it's critical. We start with pressure and oxygen as the first things on the list. If you get a hole in the vehicle, you need to respond to that really fast. Because I don't care if your water recycler is operating. If you can't hold pressure, you are done. Same thing with distributing oxygen. You've only got a certain amount of time. But water, if your water processor fails, you're not constantly putting water into your mouth. You have some period of time where you can deal with it. If you have accumulated resources, oxygen in a tank, water in a tank, you can use those stored resources during the period that it takes you to make some intervention. So when you're looking at a system that includes recycling, you're probably also looking at a system that includes stored consumables in order to bridge the gap when you have failures. And then when you think about your failures, how are you going to respond? There are some things that are going to be so critical you absolutely have to get back to full functionality, like being able to control the level of oxygen in the habitat, right? But this is where I said you have to define how critical each part of your mission is. Let's say you've decided to have a system that has showers and laundry and everything like that because you think, because they're a good mass trade, you think that the laundry system is cheaper in whatever metric you're using to evaluate cost than shipping all your clothing, and that you'll get improved performance from the crew if you let them shower. That way they are more social and they don't have abrasion, injuries and things like that. So if you lose part of your water processor, how much of that can you let go? Will you stop doing EVA because you can't recycle all the water? Will you stop doing laundry and wear the same clothes for months on end? Will you have designed a system where everybody has clean underwear packed for the same mission, but a limited number of t-shirts because you consider them less critical? You start to rank. And then some of these loss of functionality things, you may be able to accept it for a short term, but not the long term. So your stored consumables, your stored water may be based on a rate of just drinking. And your long-term plan is to really take the time to get into the guts of the system and bring it back online.
Molly?
Yeah.
This is Ollie DeVec. Hi, how are you? One question about you said the understanding system failures at the component level, there was technology choice was critical, and that makes sense. I'm wondering what your thoughts are on the side. Typically, as you make your reaction chambers, your vessels bigger, you get more efficiency out of them per unit mass, in a processing sense. But then all your eggs are in one basket. So if that unit fails, it shuts down, potentially the whole system, unless you have some totally different backup. But if you basically made it more modular and decomposed it into smaller units, then maybe 1 out of 3 units may fail, but you're still operating at 2/3 capacity. But then typically modular systems are less efficient, certainly from a mass perspective. So what are your thoughts about this? Modular versus efficiency. This is more of sort of architecture choice rather than technology selection.
We have people who do probabilistic risk assessment, right? Who try to come up with a quantitative number that can compare between options. And the thing that always bewilders me in those models is common cause failure. So there's really kind of 3 legs of that, right? One is put all your eggs in one basket. I have one water processor that does this job at full capacity. The next would be split it into several smaller groups. If you read any of the papers on the life support system for the Orion vehicle, their CO2 scrubbing is split into 3 identical units that run in parallel. And they can afford to lose one of the units, and then the crew won't be able to do exercise, but can otherwise continue the mission fine. Or lose 2 of the units, and then you start to lose your humidity control, and the crew will survive because carbon dioxide is controlled, but they need to really restrain themselves to stay comfortable and not have humidity problems. Humidity to us seems like a function thing, or it seems like a comfort thing. But for those of us in Houston, if it gets humid enough, your body loses the ability to cool itself, and you can cause serious injury. And then also, in the spacecraft, even in a warm environment like low Earth orbit or parts of the moon, you'll have surfaces that are very cold, and if there is humidity in the air, it'll start to condense on those surfaces, and then you can get water in your electronics, you can get big piles of water that allow microbial growth. Anyway, sorry, I'm off on a tangent. So anyway, the Orion has done what you said and split it into 3 identicals. But then the third option is dissimilar redundancy, where you're going to have systems of different types that provide the functions. And I think Bob talked a little bit about some of the Russian technologies. They have an oxygen generator, right? So do we on space station. They're both electrolysis. Everybody has tanks of oxygen. That's dissimilar redundancy. And then you have your oxygen candles, which are going to not require power, not really even require control. When you turn them on and start that reaction, oxygen is coming out. So if your sensors are down and your valves are all stuck, you're still going to get oxygen out of that candle. So personally, I like distributed dissimilar redundancy. But there is some detailed mathematical analysis that can go into proving that that is the right answer for your case. Does that help?
Yeah, very helpful. Thank you.
Okay, and then contingencies. I categorize contingencies differently than failures. So failures is something in my system went wrong and it stopped performing its function. Contingencies is something from outside my system happened that we have to deal with. Obviously, there are lots of contingencies that can happen in a mission, but I have a list of things that typically the life support has to help fix. So those air, water, waste, food, habitability, those same basic survival things have to happen. Depressurization is one of the first ones. You have both short-term and long-term issues here. Short-term issue, we typically talk about feed the leak. Okay, if there's a small hole in the vehicle, you need to be pumping air in as fast as the air is going out in order to maintain the pressure so that the crew doesn't pass out or die quickly. You need them to be able to get into spacesuits, get into a breathing mask, get into something so that they can make decisions and make some kind of intervention to hopefully stop the leak. After that, you need to decide what's your long-term plan. Can your vehicle be repaired? Can you get to the outside? Well, we'll assume that this is a hole that is small enough that you can identify it and see it, and it hasn't just completely split the vehicle in two. Like I said, there are some things that are just maybe not recoverable from. But if you decide that your mission is so long you'd better be able to fix a leak and recover full capacity of your vehicle, you have just basically written yourself a requirement for either sophisticated robotics or significant EVA capability to get out there and access any point where something might have gone wrong. If you aren't going to do that, you can talk about lifeboats. The Apollo 13 case, while it wasn't a depressurization, is a very famous semi-accidental lifeboat. Hank will tell you that they actually did think about the lifeboat when they were designing it, even if it's more dramatic to say it was a surprise. Where if you have your functions not only distributed, but distributed across separate volumes, you can go somewhere else to survive. Most of the architectures we talk about for Mars right now, bring the Orion crew vehicle with you. That may or may not be a good idea. But I don't think you want to live out the entirety of a Mars trajectory and return in something the size of the Orion vehicle. And so maybe, I don't know if Larry will talk about some of these. We've talked about concepts where your transit habitat is two identical systems stuck together in the middle, where you'd love to have the volume of both of them. But if one of them completely fails, at least you can survive the full mission duration in the other. So depress. Depress and the feed the leak also is one of those things that can drive you to maybe not different functions, but different technology choices and different system sizing, right? The function is always provide oxygen, but provide 50 pounds of oxygen an hour for however long is considerably different than provide, 4 kilograms of oxygen a day. Your electrolysis system is not going to be sized to pump out enough oxygen to feed a leak. So you better be able to provide it some other way. Fire and toxic release. Fire is another one of those things you kind of have to assume can happen. Most of the fires that we have seen in spaceflight experience have been due to manufacturing failures in some way. So you can say that you've designed fire out of the system, but if they don't manufacture it the way you design it, there's no promise. So you still have to be prepared for it. Someone once asked me, why don't you just remove all of the flammable materials? Well, the crew members are flammable. Their hair is flammable, their skin cells are flammable, and they're going to accumulate around the vehicle. And so unless you're going to eliminate that, you're going to have things that can burn. Toxic release is a little more dependent on your vehicle. On the space station, we have an external cooling loop that is ammonia. And so we are very concerned about ammonia getting into the vehicle. On Orion, we have a little bit of ammonia to use for post-landing evaporative cooling, so we're still concerned about it. But they've tried to change the fluid. On other vehicles, you may not have any ammonia. You may have something else. You may have propellants that you could walk EVA through if they've been around the area of the engine. Who knows? So anyway, once you've identified all those threats, again, you have kind of short-term and long-term. You have to, with the fire, the first thing you have to do, you have to put it out, right? And so Bob walked you through some of the different suppressants. Halon, carbon dioxide, water vapor, all are potentially suppressants, but then what do you do afterwards? Halon does some really nasty things in the high temperature catalytic oxygen or oxidation beds we typically use. Carbon dioxide is a little better because at least we have carbon dioxide removal systems already, but that's a lot of carbon dioxide you just pumped out. Water vapor, again, we have water removal systems, but that could be a pretty significant load you need to remove to get your habitat back to normal. And that's just the things that you introduced on purpose. Then you have all of the fire products, things made, full oxidation, things turn into carbon dioxide and water, great. But more likely you're getting pyrolysis products and partial oxidation and bits of your plastics and stuff that are burning, making hydrogen cyanide and all kinds of nasty stuff. So the ecosystem has to be sized to clean up not just the things that normally come out of the human body, but the things that unexpectedly can show up in these events. Injury, illness, or fatality. Well, Bob talked a little bit about, if the radiation is hurting the crew member, we may have to protect them more. When you're on a long mission like this, you have to start thinking about providing, let's say, medical oxygen to somebody. In the event that they're having a respiration problem. Maybe they've been knocked unconscious, maybe they have horrible pneumonia that's developed, who knows. But it seems easy, like, oh, we've got oxygen, we can just give it to the crew member. But if you take in a breath of pure oxygen, what you exhale is nearly pure oxygen, and it can really fill and overwhelm your environment. So you've created a requirement for a whole new system to deal with this contingency. Illness and fatality. Well, illness, do you have to quarantine? Do you have to come up with separable volumes to keep the crew members safe? And if you do you have to have a separate life support system? There's another spot where distributed comes into play. If I have somebody who has developed serious pneumonia in the middle of my mission, I don't want their germs circulating with everyone else. And so, but the cost of a whole additional system and a fully isolatable volume is not insignificant. Fatality. This one, is sometimes hard to talk about, but on a long mission like this, if something goes wrong, it's highly unlikely that a crew member would be returned to Earth. The human body very quickly starts to create some nasty byproducts, and those also will end up in the life support system and in the shared environment. So you have to think about how you're going to deal with some of these things. And then the last one, solar particle event storms. I know radiation, I think, has been a big part of what you've heard about so far. Within life support, we usually think about the galactic cosmic radiation as kind of always there. So either you've designed for it or not. But the solar particle events are more temporary. A lot of the plan on Orion, for example, is that they can take the stuff that they have, their bags of food, their extra clothes and things like that, and sort of assemble them into a little igloo of bags and hide in the middle. And that provides enough additional shielding to get them through the worst of a projected radiation storm. But we talked about, providing oxygen and microgravity and trying not to stick your head into the back of a rack where there's no ventilation. And now you've just created a hole where you have no ventilation, you have no access to your potty, you have no access to your food, you have no access to your water. How long is that storm going to last? How big of a volume do you need for them to survive? And what functions do you absolutely have to provide in there? And then finally, when you're dealing with contingencies, similar to the failures, how do you know it's happening in order to do something about it? You're going to hear a little bit about sensors, I think, from Daryl Jan. You need to have a detection and response system. We'll take carbon dioxide or carbon monoxide, for example. We usually have sensors for those. They come out of the human body. We're prepared to remove them. But if you have a fire, there's going to be a lot of it, and it's going to be outside of the normal calibrated range of your sensor. It may ruin your sensor. Sometimes, depending on the technology, if it goes off range, it may flood it and take a while for it to come back. So then you start having to have a normal detection option, a contingency detection option, a post-contingency detection option, and it can get a little bit more complicated. You also have to think about where you place these things when we talk about how many different volumes are we conditioning and controlling. You don't want the fire to have the smoke be ventilated across 3 modules before you detect it with your sensor, right? You want those placed close to where the event might happen. So those are just some examples. All right, finally, making decisions, right? There are a value assessment is maybe a good way to put it, but essentially you have a lot of architecture options now for providing your functions with recycling, with storage, things like that. You have contingencies that you might or might not bother planning for, and so you need to add up the costs of each of those options and decide which one provides the best value for cost. You have to. So I have a list of things that we frequently rank there, right? Mass is usually number 1. But mass of the life support system is not the only thing to think about. If you have a large volume, lightweight component, you are essentially adding to the structure of the vehicle required to house everything. And so you're adding shell mass. If you have a lightweight but high power component, you are adding to the solar arrays and adding to the batteries required. So you are putting loads on other parts of the vehicle. Crew time. Right now, crew time on space station is very important, like Bob said, because we want to use it as a laboratory, we want to use it for science, versus the submarines where the intervention happens all the time and it has a low value. On a Mars mission, you may have two very different metrics for this. In transit, maybe crew time isn't as critical. I don't know how much human science will happen during, a deep space environment phase like that. And since we'll definitely be mass constrained, that's always true, I don't know how much of a laboratory function they can send with them. But once you're on the surface, once you've bothered sending the people to the surface you want to explore, crew time probably becomes more important. You need to absolutely minimize the load. Crew functions during transit may help give them something to do and ease the psychological issues. Where do those costs occur? Okay, so I didn't specifically use the word break-even analysis, Bob, but you have to compare the cost of sending the resource to the cost of sending the hardware to generate the resource. Sending the resource is usually a linear function with time, right? The longer I'm out there, the more of it I need. The hardware usually starts with a step function to get the mass of it there, but there's also some linear components for the spare parts, for the backups, for things like that. I have in the references I have some examples of break-evens, and I'll be happy to send people more if they want them. But anyway, you have to look at both of those. And then other aspect of looking at costs, are you making an investment? Are you spending a cost that doesn't make sense for your system but makes sense for the future? We talk about sending further recycling systems to the ISS, and the International Space Station doesn't really need them, right? We're getting all that sneaky food, water resupply and wet wipe resupply, and we've got pretty good loop closure when all the hardware is working. But those resources, that spending that mass has value for our future knowledge for exploration. So if you're going to Mars, are you going to a site that anyone will ever come back to? Are you setting up something permanent and reusable? Or is this a one-time trip and whenever the next mission is, it'll be to a different location and on the other side of the planet? I'm not sure what your architecture is, but you can think about that. And once you have all those costs, you can figure out what the appropriate level of closure is and what recovery is needed in order to provide that closure. Considering the reliability of both your hardware and your stored consumables. I kind of jumped ahead to the redundancy and reliability stuff. But like I said, dissimilar redundancy I think is a good thing. Ultra-intensive testing, either on the space station, we talk about that as an approach. A lot of each of our spacecraft, while we do test them, a lot of them, it's sort of the first time that system has been fully integrated, and we have a lot of lessons learned in the first missions. And on a Mars mission, you're not turning around to go home because it didn't work the first time. When you're out, you're out. So. And then this last slide. I had mixed feelings about putting in this slide, but I think it's important, especially when, we can talk about the perfect system, but let's be real here. Cost in dollars per year usually, schedule, and contracting. If the technology is not going to be ready in time, you can't fly it. I don't care how cool of an idea it is. And the Mars missions especially usually have windows where the planet, literally where the planets are aligned, And if you miss that window and your piece of hardware is going to arrive 3 months late or 2 years late, it's a total failure. And then we had some discussions earlier about what do we know about the Russian hardware, what do they know about ours. Who's running this mission? Is it international? Is it national? Is it, is it commercial? How are you going to get these technologies? You have to have a supply chain. You have to have a way to access them. And once you've generated your list of your perfect system, and you start running into these issues, you have to figure out which ones you're going to fight for the most. And I know, this is all about innovation and stuff like that. And I'm not here to beat you down and tell you you can't do the good idea. I want to emphasize the engineering challenges, the devil's in the details, and all these things to make these systems possible. I really hope that we will get new and doable ideas out of these efforts. Do a time check. Am I about out of time, I think?
You have about 3 minutes, I'd say.
Okay. So just example architectures you can look into. The spacesuit system is one that's highly dependent, right? They don't do a lot because they siphon everything off the vehicle. Their LIO, their water sublimator is all based on lightest on the back mass, not life cycle mass. Space shuttle is another one that's kind of in between. We have a lot more functions because we have a longer duration. Life support gets to siphon resources off the propulsion system with the cryogenic oxygen. We have some consumables that are not regenerated because we have a nice supply chain to Earth. Space station, we have a much longer life cycle, so there are a lot more trades towards recycling. But at the same time, like Bob said, there's still a pretty strong supply chain to Earth for the parts to make that happen. I'm not sure how much detailed work everybody is doing here. I'm going to go through some of these. I'm not going to go through the documents, obviously. This Human Integration Design Handbook is a really great resource. It's publicly available for people to get into. The Baseline Values Assumptions document is something that my team has published that goes into more information about designing the life support system versus just what does the human need in and out. So it has more information on recycling and stuff like that. This 1997 paper is a good description of what people thought the closed loop ISS recycling ECLSS would be like, and so you can go through some of that rationale. Living Together in Space is another great publicly available document that goes through the ISS architecture and the life support. A lot of the NASA life support community publishes updates at the International Conference in Environmental Systems. It was an SAE conference for a long time. Now it's AIAA. This one's actually a paper I wrote about lunar lander issues. This one's lunar lander issues. This one is a paper Dr. Kevin Lang wrote about lunar surface colonies, where we go through all of those trades and issues that make you swing your decisions one way or another. So if you have specific questions or want examples, I'll be happy to help set people up with papers. But like I said, if you have a speaker and you try Googling them in either of these or finding them in either of these conference archives, you'll probably find some good papers. Attached to the back, I have just these sort of sweeping ideas for the evolution of life support systems and NASA's thoughts and plans on how we would evolve towards Mars level capability. But I don't want you to assume that we have all the right answers, right? I mean, the goal of this is for you to find your own innovative way to do things. Questions? I think that's the end.
So,
Yeah.
one question is, like, there are all sorts of differences, like when you deal with microgravity and gravity. Let me ask a simple one. How does an astronaut take a shower in, say, the International Space Station?
So there is no shower on the space station. They try to shower on Skylab. You can put water pressure behind a nozzle and spray water in microgravity. We have spray cooling. But then they had to vacuum the water off of the surfaces, including themselves and the plastic curtain surrounding them, and that took about 2 hours, I think, and your shower was only like 2 liters of water, and they decided it was not worth it. So what we do now typically is for body cleansing. Well, Charlie probably has even more details on this. You can dispense the water directly onto a towel and do a body wash with a wet towel as opposed to a shower. I think we have no rinse shampoos, which are questionably effective depending on your hair. I've heard stories of people loofahing themselves with pieces of Velcro to slough off the dead skin before they wipe down. People are very innovative.
Innovation right there.
Zero gravity waxing.
Thank you.
Molly, that was fantastic. Thank you so much.